Hello everyone and welcome to the second video dealing with the spring break packet from 2019 that I gave you on the last day that you were in class. Anyway, let's get started. Remember, the format of this particular free response section is the exact same as what is currently done. So this is still a fairly recent free response. So the first two questions are calculator questions, and then the last four are non-calculator questions. So let's get started on question number one. Question number one on this one, they're talking about rain going into, the rate at which rainwater is flowing into a drain pipe is modeled by this. So this is the rate that's going in, and then the pipe is partially blocked, allowing water to drain out the other end at a rate that's modeled by here. So you have to keep in mind both R of t and D of t are rate functions. Okay. And this is for t going from 0 to 8. And again, they go through on this one and they give you this part right here where there are 30 cubic feet of water in the pipe at time equals 0. Now, the thing you have to keep in mind on this one of the important concepts that they're looking at here is keeping in mind the difference between, if we look at it in terms of the velocity, the distance versus displacement. Remember, we talked in class about how the definite integral, the definite integral velocity is going to be a displacement, while the definite integral of the absolute value of velocity, or the speed function, will give you a distance. So that's really what you got to have to keep in mind here. So the first question here, how many cubic feet of water flow into the pipe in the 8-hour time interval? That's pretty self-explanatory. Again, this is really looking at the displacement aspect, not overall. And then is the water in the pipe increasing or decreasing at time t equals 3? Give your reason for that answer. Okay, now this is where you have to keep in mind what you're told up here in the beginning. The rate at which water flows in and the rate at which the water is going out is modeled by these two functions. So be careful with that in terms of determining whether or not the amount of water at time t equals 3 that's in the pipe is increasing or decreasing. At what time t does the amount of water in the pipe have a minimum? Okay, now keep in mind, again, the amount of water in the pipe, you got to think about how it's changing. Hint, think about B, and set up a function that you can use to model how much water is in there. Now, you do have to keep in mind, because this is a closed interval that you're working on, 0 to 8, you do have to keep in mind the endpoints, but you also have to look at other critical values, any place where the derivative of the amount of water in the pipe is equal to 0 or undefined. Okay, and then the pipe can hold 50 cubic feet of water before overflowing. For some value t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives us. So in this case right here, again, this is a problem, part D, of these four parts in problem one. Part D is one that can actually, you don't need your calculator for, because you don't have to solve it. Be aware of that when they tell you, write but do not solve. Because if you try to solve something like that, all you're going to end up doing is taking up additional time that you can be using on something else. So in this case, just write. They want you to write but do not solve. And I would go through working on number one. I would do parts A, B, and C. The minute I saw it says write but do not solve, I'm going to save part D for when I have more time, either in the first 30 minutes if I finished up part 2 completely, or problem two, or at the end when I'm working on the other 4 if I've finished those ones up completely. All right, now we look at question 2. Question 2 is a BC question because you're dealing with the parametric equations here, or in terms of this. So what you're told here is at time t equals 0, that a particle is moving along the curve in the xy plane and has position x of t, y of t, with velocity vector here. At t equals 1, the particle is at 3, 5. Now, again, you have to keep this part in mind. That's there for a reason, okay? Because you have to remember when I'm going through and trying to work with this, any integral of these functions is going to result in a displacement. You've got to use where you're initially starting. So the first question you have, find the x-coordinate of the position of the particle at t equals 2. So keep in mind that in this case, they're using vectors here, but you can also look at it as parametric. X of t, y of t here, this is your velocity vector. So you know this is x prime of t, and that's y prime of t. So you can go use that information and the fact that t equals 1, you know x is 3, to go through help you out determine when this is going to be 2. Now, for this next part, for 0 to 1, t going from 0 to 1, there's a point on the curve at which the line tangent to the curve has a slope of 2. At what time is the object at this point? So again, keep in mind what the slope is. You're looking at a curve in the xy plane, so you're trying to find dy dx. Think about what you know right here to help you do that. And then you have to find the time at which the speed of the particle is 3. Speed. Remember, speed is the magnitude of your velocity. Okay, the amount of speed is going to be the magnitude of your velocity. Every vector can be written as a product of its magnitude and its unit vector. The unit vector is going to give the velocity vector its direction. So in this case, the magnitude of your velocity vector is going to be the speed of your particle. And then the last part here, find the total distance traveled by the particle from time t equals 0 to t equals 1. In that part right there, really what you're looking at, if you were to graph this thing out, you would, if you had the graph, okay, whatever this happened to be, I'm just going to draw a curve. I don't know what it actually looks like. But at t equals 0, we might be at this point. At t equals 1, we're going to be at this point. What they want is they want to know that distance that you've traveled. That looks a lot, and it is really looking at the arc length. So keep that in mind. In this case, on this problem right here, they want that total distance traveled. You're really looking at the arc length that was of the that the particle traveled along. Okay, so that's something to be aware of on this one. One other thing to keep in mind on this particular problem is that really each one of these here, there was not a time when I would necessarily sit there and say you could go through and do a part of this problem without your calculator. Now, you could go through, if you ran out of time on it and you weren't with your calculator and you weren't able to finish it out, please make sure to put down the integrals or whatever you can do, because you'll get points. Like here on this one right there, if you have the integral set up, but you aren't able to evaluate it, you got 1 point. Same with this one right here. If you had the speed, if you had an expression that represented the speed of the particle and you set it equal to 3, that got you a point on that one. You know, the equation that you would have solved. And that's going to be the same for each one of these other parts. As long as you get the problem set up, you have the something that you can work with. So please try to, if you run out of time, try to make sure you get those things put down. These next two questions, 3 and 4, are again they are AB questions, so these would be common to the AB exam. Number 3 in this one, you have the Johanna is going on a straight path, and from t going from 0 to 40 minutes, her velocity is given by a differentiable function v. Okay, and so selected values of v, where t is measured in minutes, is given in the table above. So at t equals 0, her velocity is 0. When t is 20, her velocity is 240 meters per second. Notice at t equals 24 minutes, her velocity is a negative 220. So you got to keep that aspect in mind. Remember, velocity does give you speed and direction. Okay, so on this one here, use the data on the table to estimate the value of v prime of 16. That's pretty. That's become a fairly common question when they're giving you table data. There was one time when they used to go through and say, oh, they'd want you to go and say estimate something like v prime of 20 using that. And there was multiple answers. Now they're going through and using a number that's going to be kind of halfway between two of the values that they're given. So in this case, you know the velocity at 12 and 20. 16 lies right down the middle. So your good estimate of that is going to be an estimate. The good estimate of the acceleration at t equals 16, which is the derivative velocity, is going to be just kind of finding a slope. Okay. Using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t in the context of the problem. Okay, so you have to be aware of units. Remember, an integral, when you're finding an integral, you multiply the units. If you're finding a derivative, you divide the units. So in this case, this integral is going to be the units of v of t times the units of t. So that gives you that aspect, but please keep in mind what they're asking for here. You do have to explain the meaning in the context of the problem. Okay? They want you, so that's just what that means. Then they want you to approximate it using a right-hand sum with the four subintervals there. So make sure you're comfortable with approximate. You're using a right-hand sum. So you have one interval from 0 to 12, one from 12 to 20, one from 20 to 24, one from 24 to 40. And you can go through and, again, you're using a right-hand sum. Now we have Bob is riding his bicycle from t equals 0 to t equals 10. Bob's velocity is modeled by this particular function where t, again, is measured in minutes, and b of t is measured in meters per minute. Find Bob's acceleration at t equals 5. It's pretty. This is your velocity function, and based on this model from part C, find Bob's average velocity on the interval from 0 to 10. Okay, so again, you got to use the whole idea of the average value of a function. The average value of a function for any function is going to be the integral from a to b of f of x dx, and you're going to take that and multiply it by 1 over b minus a, or some people will write it as the integral from a to b of f of x dx all over b minus a. Either one works, but it's up to you which one you want to work with. Anytime you see an average value of a function, that's really what you're looking for on that one. Now we have a differential equation and slope field problem. So in this case, as you've seen in the past, often in a problem like this, you're going to find that these problems have a lot of points that are going to be put later on dealing with the particular solution and so forth. So in this case right here, we have that dy dx is equal to 2x minus y. And so on this axis, they're going to want you to sketch a slope field for the given differential points at the 6 points that are identified. So we have these 2, 4, 5, and 6. So make sure you're careful with those and you look at where those are at. So you go through and work with that. Then the second one here. that's usually going to be 1 or 2 points. In this case, I think it's going to be 2 points, just because you're going to have slopes where it's 0, or slopes when x is 0, and then slopes where y is equal to, or where x equals 1 in this case, because that they are looking at those two values. Sometimes they look at it where the slopes are 0 and where the slopes are whether or not the slopes have this correct sign. Please also be aware that they're not going to be super picky about the steepness. Okay, you want to try to make it there, but often when the steeper it becomes, the harder it is to really make a distinguish between them. So if it's as long as it's really going through, when you make your sketch of your slope field, as long as it's relatively close, you're going to be okay. The second part, they want you to find that second derivative. Okay, in terms of x and y, please remember that when you do this, you got to think of the chain rule, because this will be, when you take that derivative, you got to deal with the fact that this is a function of x. Okay, so think of the chain rule as you're working on that one. And then you have to go through and determine, in this case, they want you to look in, for all solutions that are given a differential in quadrant 2, what the concavity is. So think about what's true about points in quadrant 2, and then make your determination about what's going to happen with the derivative on that, the second derivative for all points in quadrant 2. Next one, let y equal f of x be a particular solution to this differential equation such that f of 2 equals 3. Does f have a relative minimum, a relative max, or neither at x equals 2? So what you're going to have to do on this particular problem to make that determination, the issue comes in because you have this differential equation. You don't know what f of x is. And really, to go through and solve this one, this is a little bit different from a lot of the differential equations you see in the other problems, because this is one that you're not going to actually solve, okay? But on this particular problem, you've got to use the fact, you got to go through and come up with a different way to do an analysis. Now, we want to determine relative min, relative max, or neither, okay? Well, we know it has this particular solution there. One of the things you can do, remember on this one, in order for there to be a relative min or relative max, then the derivative needs to be a 0 or undefined. So just plug that point in, see if that works out. If that, in this case, it's very quick to see what actually happened, so it's easy to make your determination. Let's say, though, that it did equal 0. If it did equal 0, then in this case, I would want to go back up to part B to make a determination on its relative max or relative min. Remember, if it's equal to 0, you do have the second derivative test for extrema that can come into play as well. So you want to be looking for something like that to occur as well. So if you're not able to make a determination in terms of the function, to look at whether or not so you can tell if the derivative is increasing or decreasing at a particular, or is positive or negative at a particular values, then you want to look at that second derivative test, see if that can come into play. And then here, find the values of the constants m and b for which y equals mx plus b is a solution to that differential equation. Remember, dy dx equals 2x minus y. So put 2, you got 2x. If y equals mx plus b is a solution, just put that right up in there. And you know dy dx on this one, the derivative of that is just going to be m. So that gives you a solution, an equation that you can then try to solve. So that really gets you through question 4. I hope you were able to go through and get most of this, if not all of it, previous to this video. Now let's look at question number 5. This one is going to end up being this is a BC question. So we want this function. We're told f of x is equal to this, where k is a non-zero constant. The derivative of f is given by this. So notice they're not actually asking you to find the derivative, although it would be very quick to find it. They're just telling you what that derivative is. So the first one they have here is let k equal 3 so that f of x is equal to this. Write an equation for the tangent line of the to the graph of f at the point where x equals 4. Well, they've given you the form of the derivative, so then you're able to go through, you know, k is equal to 3. So you plug 3 in for k and 4 in for x. That will at least give you the slope, and then you plug 4 back into this. That will give you your point. You're able to give me the equation of that derivative, okay, or the tangent line. And then here, let k equal 4 so that f of x is equal to this. Determine whether f has a relative min, a relative max, or neither at x equals 2. Justify your answer. Okay, so on that particular one, you're going to need to go through. If you're going to have a relative min or relative max, the first thing you really need to do when you see relative min, relative max, you know you should be looking for f prime. So you're going to want to do that, make a determination from there. If it's even a possibility, when they're giving you or neither, it is possible that if you plug the 2 in to the function that you're not going to get 0 or something is 0 or undefined. So always find that derivative and then plug that 2 in, see what happens. And then based on that, once you have the derivative, you can use if it does come out to be 0 when you plug in 2 or undefined, you can then use the first derivative test for extrema to determine whether it's a relative min or relative max. Or again, it is still possible to be neither, because it could be graphically, it could do something like this, where you have there, so there's 2, and graphically come up, level off, and then go like that. Or it could do this at 2. So we could have something that's going up and then gets very steep and then goes like that. So those would be two situations where the derivative would be undefined in this case, or would be equal to 0 at 2, but we don't have either of those, either a relative max or a relative min. The third part here, find a value for k for which f has a critical point at x equals -5. So really, you want, when you let x equal, when you plug -5 in for x, you want this to be 0 or undefined. Okay, so that's what you're really looking for on that one, is values that could make that equal 0 undefined. Then what happened? The next thing you have is let k equal 6. Here you got to use a partial fraction decomposition. The nice thing, remember though, what's required in terms of partial fraction decomposition. When we looked at these, we looked at it having linear factors, repeated linear factors, irreducible quadratic factors, repeated irreducible quadratic factors. The nice thing you have on this for this particular exam is if you're looking at all those different cases, when you're doing partial fraction decomposition, you are using non-repeated linear factors. And sure enough, this right there will factor, that will factor as, x squared minus 6x factors as x times x minus 6. So you're going to go through and use that fact to break this thing down using partial fraction decomposition, and then integrate that to get to find an expression, an indefinite, an expression for the integral of f of x dx. Notice you don't have any limits of integration, so you're not going to get any particular value, but you do have to have that. Also, it is the general antiderivative, so remember, don't forget plus c in that one. Okay? Now let's take a look at question number 6. In this case, question 6, we are told we have a Maclaurin series. This is function f, and they give you the first parts of the expansion. They give you the general form of that, and we know it converges to f of x for the absolute value of x less than r, where r is that radius of convergence. You've seen this before. Now, the first thing they want you to do is use the ratio test to find out what r is. Okay, so make sure you go through and do that. And then the next one, they want you to write the first 4 non-zero terms for the Maclaurin series of f prime. Remember, you're taking the Maclaurin series for f. If you want the Maclaurin series for f prime, just take the derivative. Now, the nice thing is, hint, they give you the first three terms here, and the derivatives of each one of these first 3 terms are non-zero. So you just have to identify what that next term would be, and that would then give you the first 4 non-zero terms of their f prime. Now, the next thing they also want you to do on this one is express f prime as a rational function. Well, the thing that you're going to want to do on this one is once you go through and find that derivative, you need to take a look and see if you can find a pattern that exists there to go through in terms of the type of function you're working with there, and see if you can use that. Hint, you might notice that it's a geometric. You might notice some sort of geometric series happening there. And we know that it's going to converge when the absolute value, a geometric is going to converge when the absolute value of r is less than 1. And we know, again, that the sum of a geometric series is equal to the a1 over 1 minus r. So we might want to use that to help us out in terms of expressing that as a rational function. And then the last part here, write the first 4 non-zero terms of the Maclaurin series for e to the x. So this is one that you need to remember. And then use that Maclaurin series to write the 3rd degree polynomial that will be the product of those. So you're just going to go through, write this out, and write out the e to the x, and you want to multiply the terms and combine the like terms all the way up. You want to make sure you want a 3rd degree polynomial for Taylor polynomial for this. So you want to make sure that you include everything that is going to be, that will multiply to be less than or equal to a 3rd degree expression. So anyway, with that, this does conclude the second video dealing with the last 6 problems of the spring break packet. I hope that you've had some fun going through working on these things. I think they are kind of interesting. And we'll see you in a couple of days. Enjoy these last 48 hours of spring break.